Hello and welcome. I'm going to go through the solutions to quiz 45 in this video. So we have 3 liters of O2 with a pressure of 2 atm at 25 degrees C being mixed with 2 liters of N2 that's at 1 atm. What is the partial pressure of O2 once the mixing is complete? Now, you can do a few things here to think about this problem. You could calculate the moles of O2 present here, and then just simply then take that number of moles with the ideal gas law, with our new volume being 5 liters that the oxygen has to occupy once this valve is open. So once we mix the two gases, oxygen has 5 liters of sample instead of just 3 liters. And so another approach would be just using Boyle's law, that P1V1 equals P2V2, or pressure and volume inversely related, so we get this relationship here. We could also get that by inspecting the ideal gas law and thinking about the moles of O2. The temperature are constant, so the only variables here are pressure and volume. So really we're just expanding from 3 liters of oxygen to 5 liters, but keeping the pressure adjusting to keep the two equal to each other. So we can solve for P2, 1.2 atm. Some versions of this question might ask for the total pressure. If this question said, well, what's the total pressure once the valve is open? It's not 3 atm. You don't just take the two pressures and add them together. You have to take the partial pressure that oxygen has, 1.2 atm, and then calculate the same sort of expansion for N2 into 5 total liters. I think it ends up being 0.4 atm is nitrogen's partial pressure. Then you sum the two together. So remember, if you need to sum up to a total pressure, you take your two individual partial pressures to sum up to your total pressure. So you might use this approach if you need to calculate the total pressure. Question 2 is asking which molecule would escape from a pinhole the fastest. That's going to be the lightest gas particle because it has the highest root mean squared velocity, or the highest average velocity. So the substance with the lowest molecular weight has the highest root mean squared velocity. So that one would be helium. Number 3, which molecule most likely has the greatest Vanderwall A constant? The A constant, you might have to inspect the Vanderwall's equation to see that the A is the one that's affecting the pressure, and B is the one that's affecting the volume. So B is proportional to the size of the molecule, and A is the one that's related to the intermolecular force strengths between the particles. So molecules that are more polar, and also molecules that are just net bigger than each other, have larger A constants. So if molecules are relatively the same molar mass, or close to the same molar mass, we're looking for the more polar substance. So water is going to be the one with the greater A value, since it's the only substance in the choices that's a polar molecule among these choices, and they're all relatively small molecules. If we give you a really big molecule, something like CCl4, it ends up having a really big A value as well due to its large size. So sometimes the size becomes a factor in making A bigger, so we have to be careful in the choices we give you. So realistically, you're just looking for the polar molecule or the most polar molecule if given a selection. We'll be getting into polarity of molecules in the next chapter to get a greater sense of what makes a substance have greater versus lesser intermolecular forces. Now, the substance with the larger B value is going to be the molecule that takes up more space. So we're kind of thinking CH4, relatively small bonds here, oxygen much bigger atom, longer bonds, oxygen takes up more space. It's kind of a tough comparison to make. Probably CH4 and CO2 are the two that you might be down to, because CH4 is definitely bigger than water, definitely bigger than neon. O2 kind of in that same mix, so O2 is definitely going to be smaller than CO2 though, so put a carbon between the two oxygens, definitely CO2 is bigger than O2. So we're down to CH4 and CO2, and it ends up being CO2. Kind of hard to make the comparison. I think CH4 has relatively small CH bonds, the CO relatively bigger in terms of the atoms. I might prefer if this choice had said something like CCl4, where chlorine's bigger than oxygen, you have more of them, clearly then CCl4 would be the bigger molecule. So I think choices here make this question a little bit tricky, but it's just trying to get us to think about the relative size of the molecules, which individual molecule or particle takes up more space. Number 5, we have a vessel that's filled with a certain quantity of substance, and then the pressure of the vessel is known, the temperature is known, the volume of the container is also known. We're asked to figure out the molar mass of the substance in grams per mole, and in order to arrive at the particular answer, what we need to do is maybe use an equation that looks like this. We get this equation from the ideal gas law, PV is equal to nRT. We sub in mass over molar mass for moles, because moles is just mass over molar mass, and we just simply solve for the molar mass. So you can derive an expression like this one pretty easily just from the ideal gas law by subbing in the mass over the molar mass. And then we're just plugging in and solving from there, making sure we convert pressure to ATM. Volume should be in liters because we're using our R in ATM times liter divided by mole Kelvin. So we got to have our temperature in Kelvin. And then our mass can stay grams because we're calculating the molar mass in units of grams per mole. So for the second page here, so number 6 says which statement is true of a sample of CH4 gas at 298 Kelvin according to the kinetic molecular theory, the theory of gases. So the first choice says all molecules in the sample have identical kinetic energies. Now that's not true because we get a range of speeds of our molecules. So the molecules have a Boltzmann distributions of speeds, and the speed is simply connected to the kinetic energy. The kinetic energy is equal to 1/2 mv squared. So if we have a range of velocities that the gas particles have within a sample of methane, then we're going to have a range of kinetic energies that their particles have as well. So all the particles do not have identical. They have a range of kinetic energies that's described by a distribution. The molecules in the sample also therefore do not have the exact same velocity of each other. They have a range of velocities. And then we describe the most probable versus the average versus the root mean square velocity. And we can calculate the most probable and the root mean square by using the square root of 3 RT divided by molar mass for the root mean square, and the most probable is 2 times RT divided by the molar mass. So anyways, the other choice is C, says the average velocity of the molecules in the sample is less than that for a sample of CH4 liquid. CH4 liquid would have the kinetic energies greatly reduced from the gaseous particles so that the particles can condense into the liquid phase. So the liquid have lower kinetic energies, not the gaseous particles. So statement C is incorrect. D says the average velocity of the molecules of any sample is identical to their most probable velocity. So the average velocity of the molecules is not the same as the most probable because we get this unweighted or this non-parabolic distribution. We get a weighted Boltzmann-like distribution where we have more molecules on the faster side, fewer molecules on the slower side, so the most probable or the average speeds don't overlap with each other. So the average velocity of the molecules in the sample is not identical to their most probable velocity. Those velocities are slightly different from each other. And then finally, the last statement hopefully should be true because it's the only one left, but the average kinetic energies of the molecules in a sample of O2 is identical to CH4 at 298 K. So if you have two different substances at the same temperature, their particles on average have the same kinetic energies. So the kinetic energy is a constant. Kinetic energy is 1/2 mv squared, so that's a constant for any substance at the same temperature, so that a more massive particle is going to have a slower velocity on average. Okay, so the average kinetic energy of the molecules in a sample is identical as long as they're at the same temperature as each other. And then if the temperature increases, the kinetic energy just simply goes up. And you can see how this relates to the velocity if you just think of the 2 or the 3 RT, depending on which value you want to calculate. Let's say you calculate the root mean square velocity. The VRMS equal to 3 RT divided by molar mass. So if you increase temperature, you increase the root mean square velocity. If you increase the molar mass, then you decrease the root mean square velocity. You can think of the relationships the molar mass and temperature have and the velocity of the particle, and then the velocity of the particle times the mass of the particle give you identical kinetic energies provided the samples are at the same temperature as each other. Moving on to number 7, we have a few Vanderwall's A and B constants that are listed, and we're trying to identify which one is argon, which one is CO2, which one is ethanol. And so argon is the smallest of these three in terms of it's just a single atom. All three of these, like argon's about 40 AMU, ethanol is about 46 AMU, CO2 is about 44, so they're all about the same size. So argon being a single atom should give it the smallest B value, and it's also nonpolar and also, again, pretty small in terms of its actual molecular size. That's going to point towards B being argon. And then A has the largest A value, the greatest intermolecular force of attraction, also the most space occupied by the molecule. That really looks like ethanol. That's a good choice for ethanol because ethanol is the only choice of these three that's polar, so it should have the largest A value. And then it also has many more atoms to spread its space out, so the molecule of ethanol is likely going to take up much more volume than a more compact 3-atom structure for something like CO2. So CO2 is likely C, argon is B, and then ethanol is choice or compound A in this example. Number 8 looks at which statement is about gases is true. Equal volumes of ideal gas at the same temperature and pressure contain different numbers of molecules, while ideal gases of equal volumes contain the same number of particles. So the particles are the same for ideal gases, so A is incorrect. The volume of a fixed quantity of an ideal gas maintained at constant pressure is directly proportional to temperature. Volume and temperature are directly related to each other. Increase the temperature, you're going to increase the volume of a gas, the moles and pressure being equal or constant throughout that process, so they're directly related to each other. PV is equal to nRT, so volume, temperature directly related, not inversely related. The average kinetic energy of gas molecules is greater than the energy of attraction of the gas molecules. That is correct. So the average kinetic energy of gas molecules is indeed greater than the attraction of the gas molecules, because if the attraction of the gas molecules was greater, then the substance would have existed as a liquid instead of a gas. Okay, so for a substance to exist as a gas must mean that the substance has a greater kinetic energy as a gas than it would as a liquid. Statement D, the standard temperature and pressure, 25 degrees C, 1 atm, well, standard temperature is 0 degrees C, not 25. That's something you got to know. In statement E, in a given sample of an ideal gas, gas molecule behavior is dependent upon molecular attraction and repulsion. In an ideal gas, there are no attractive or repulsive forces present. So ideal gases do not have attractive or repulsive forces. That's what makes them ideal. Number 9, oxygen gas being generated from a reaction. Here we have to sort of realize that we're generating a mixture of gases, of water vapor and our O2 from the chemical reactions. We have to subtract off the water vapor from our total pressure to get our partial pressure of O2, 727 torr, convert that over to atm. Plug that then into the ideal gas law so we can calculate the moles of O2 that are present in the particular volume at the given temperature of that gas sample. So we calculate the moles of O2, 0.0777 moles of O2. We then just have to convert that over to grams of KCl3. Using 3 moles of O2, need 2 moles of KClO3 to form them, and then we just use the molar mass of KClO3. I readjusted this number. I think it came out to 6.35, so the version you have should have a slight revision in choice B that matches the values you should be calculating. And finally, number 10, the root mean square velocity of a sample of ammonia at 245 degrees C. We're just using 3RT divided by molar mass, but we have a unit problem we got to pay close attention to. So with our units here, we want to use, we want to calculate a root mean square velocity in the SI units of meters per second. So we're going to plug in and use the joules per mole Kelvin. A joule is a kilogram meter squared per second squared. 8.314 kilogram meter squared per second squared per mole Kelvin, multiplied by the temperature converted over to Kelvin. But you've got to divide by the molar mass in kilograms per mole in order for the kilograms to cancel into that base unit of kilograms behind the joule. So you just either have to remember or plug in your units so you can see that you need to plug the molar mass in units of kilograms. You end up getting 871 meters per second here for the answer. All right, so that's the solutions, or a video of the solutions to this quiz. Thanks for the attention.